So today we are going to wrap up the driven and damped oscillation part. And we are going to see that we can actually get analytical solution for the part which has an applied force to the system. And that's also extremely useful because we can then look at the numerical results when we run calculations, and we can compare that with analytical calculations and try to explain to ourselves and other people what is actually going on and why we see this specific behavior. So let me just quickly remind you of what we got on Monday, and then we're going to look at the solution of the equations with an applied external force. So you are not limited now to a system with a harmonic oscillations with a spring only. You could think of this as a pendulum. You have the mathematical pendulum. You can make more complicated systems. You can look at this when you come to a course in electromagnetism. You would meet the same type of equations when you have what's called normally an RLC circuit. And some of you may already have seen this kind of differential equations for that type of system. So when you're solving the equations now, this is something by a change of constants you can actually bring with you to other physics courses. And that's extremely powerful when you have developed algorithms for solving these type of equations. So let's look at the mathematics again. So what we had is a differential equation which we wrote in terms of dimensionless variables. So we introduced this parameter omega, which was given now in our specific case by the spring constant divided by the mass of the object. We introduced a dimensionless time, which is now given by this omega times t. And then we could scale the equations. We also had introduced another parameter, which was given by b divided by 2m times omega 0. So in the literature, this is often called the Q term, and some people also call it the quality term. I don't know whether that has to do with the quality of the solution, but we are coming back to that when we're going to interpret what this actually means. So the equation we are looking at when we scaled it is something like this. We are looking at things in one dimension, but there's nothing which now limits us to just stay in one dimension. So we had this parameter gamma. We had the first derivative, which is the velocity. So this is a damping term. We had plus x. And what we looked at on Monday was a case where we had no applied force, but the general equation would now be an equation which was given by a force which has an amplitude, which we had scaled, as we did on Monday. And then we had something like a cosine. Now, keep in mind that this doesn't need to be a cosine. It could be a sine, or it could be some other type of applied engine, which you apply to the system so that it can actually oscillate back and forth through time. And then we had some scaled frequency here, which was now given by a tau. So this was the type of force which we had. And this omega tilde was then given by the original frequency of this engine divided by omega 0. So we had a scaled frequency. So everything is now dimensionless. And the thing which is nice with making the equations dimensionless is that you can actually bring this to another physical system. Now, what we did on Monday was to actually say that f of 0 is equal to 0. And that type of equation, when we put the right-hand side equal to 0, that has a name. And for those of you who have done differential equations in math courses, is anyone who remembers what we would call a differential equation when we only have quantities which we involve the unknown parameter x? So x is the unknown quantity. So when you look back at differential equations, this typically has a name when you put it equal to 0. Does anyone remembers that? Let me see now. We have this table and that table. They always answer, but I think I don't want to penalize you guys. But we have a new, yeah. Say it again. Homogeneous, yeah, right. Yeah. It's a homogeneous equation. But then when we add this special case, it gets a new name, right? So anyone who remembers what it's called then? I think you know it, yeah? Yeah, that's, you could say that, but if we have a special term, it's normally called the special solution, because then we actually specialize it, or the particular solution. Is that the name you've heard? Particular solutions? Yeah, because now we are setting in a particular right-hand term, and then we are seeking a particular solution. So the homogeneous one is normally when we have just the unknown quantity, and then we put in something particular. So you could also see it as an inhomogeneous or special, but it's normally called a particular. So let's look at the solution first, which we got on Monday. So on Monday we had, this was something which we call the homogeneous equation. And what we did then was to show, without now being too specific, we found that this x of tau was given by a constant A1. And then we had an e to the R1 times tau. And now we don't specify whether R1 or 2 are imaginary or real. So as you saw on Monday, we could have imaginary solutions as well to this R1. But now we're just going to leave it like it stands. And this R1 and R2, they could be complex or they could be real. So R1 was given by this gamma plus gamma squared minus 1, whereas R2, as we found on Monday, was given by minus gamma squared minus 1. And then depending on the value of gamma, we could get an imaginary component, or it could just be real. And then we had 3 cases, which we looked at on Monday. So we had the case with gamma less than 0. That gave us a so-called underdamped solution with oscillations. No, sorry, not less than 0, but less than 1. Less than 1. And then we had gamma equal to 0. Now, why do we insist on 0? I don't know why. I don't know why. Sometimes things just pop out against your will, right? So this is called critical damping. And then we have gamma larger than 1, which is called overcritical damping. So this is basically what we did on Monday. And then we analyzed different cases. Now, what we're going to look at now is the particular solution. And in the case when f of 0 is different from 0, we are now looking at the particular solution, xp of tau. And this is normally called the particular guy. So if you now look at the term which we have inserted here, if you look at this f0, remember now that when we approached the solution for the homogeneous case, we actually guessed that this solution may have something with sine and cosines and exponentials. If you now look at the particular one here, what is your guess? What kind of solution would you guess for the particular one? If you look at the term which we have applied to the right-hand side. So we know the homogeneous, yeah?
Oh, yeah, probably involves cosine and sine.
Yeah. So let's now make a guess. So we assume now that the particular solution is a cosine. And let's insert that in the equations and see what pops out. So remember now that what happens when you have a particular solution is that you have to solve it for every specific case. So if I plug in a sine or another type of engine which drives the system, then I have to search another particular solution. So the homogeneous case is something which you can always write down in a general way, whereas a particular case is something you have to seek for every specific case which you have. So since we have a cosine, let's guess on a cosine. So, and what comes now is just mathematical manipulations with sines and cosines. That's nothing more than that. So let's do that. So we make a guess now. And our guess is based on what we have on the right-hand side. So we simply say that we assume that this is given by an unknown constant, d, and then I have a cosine. And since I have this omega tilde, I take omega tilde times tau, and then I can add an unknown constant, which is a phase. Like we saw on Monday, when we did the mathematics, we could actually rewrite the solution in terms of a cosine, and then a frequency, time, and then some phase, which we can decide when we are solving the equations. So the procedure now is just to insert this ansatz or this guess into the equations. So what you would do then is simply to plug it in the differential equation, plug in to the ordinary differential equation. I write this as ODE. That's ordinary differential equation, and that means the equation which we have up here. So we go back to the equation. So we are now just plugging it in here and see what happens. So when I plug it in, what I get then is on the left-hand side, I get a D. So now we're going to have to be careful with what we're doing. So we have a second derivative. So that gives us a cosine. So we're plugging in the particular solution. So we have an omega tilde times delta, not tau, minus this delta. I get a minus. So this is the first derivative. I have an omega tilde. This is obviously a sine of tau minus delta. And then I get a plus cosine. Minus delta. And this has to be equal to F0 tilde of cosine of omega tilde tau. Okay, it doesn't seem as we have done much here, except setting it in. Now, what comes now is just a manipulation of cosines and sines equations. So we need some of these standard trigonometric relations. So there's nothing, how to say, exciting about this. It's just an exercise in using trigonometric relations. So I just want to demystify that this is not, we have some manipulations, but it's, so if we use the well-known expressions here, we know that this can be written as a sine of alpha of cosine beta plus minus a sine of beta times a cosine of alpha. And we have a similar one for the cosines of alpha plus minus beta, which is then equal to a cosine of alpha, a cosine of beta, and this is a minus plus of sine alpha of sine beta. Now, if you now look at what we have in the equation, which you see up here, the one in the differential equation, we actually have a cosine with an omega t minus a delta. So that means that we could actually use the cosine alpha plus minus beta. And then we have a sine, so we could actually plug in that expression for the sine. And then what you're going to see now is that you will get one expression which contains cosines only and one with sines only. And with those equations, we can require that the sine part should stay the same for all times and the cosine parts the same. And then we can, when we identify these different terms, we can then find this d, and we can also find this term delta. So let me just go through these calculations here. So what we do now, when we plug it in, we need to do some algebra here. So we get a d, and then we have a minus. So this is the cosine piece. So it's going to look a little bit ugly. A cosine delta plus 2 times gamma of omega tilde of a sine delta plus a cosine delta. And this is multiplied with a cosine of omega tau. And then we have the sine part, which goes like plus minus. And then we have an omega squared sine delta minus 2 times omega. And then I have a cosine delta plus a sine delta. And then I have a sine of omega of tau. And this is all equal to f tilde times cosine of omega of tau. Now, what we need to require now is that the cosine parts have to match each other for all times. So the cosine solution, which you see here, if you look at that one, so there's a cosine term here, and there's a cosine term here. So we are going to require that the cosine terms have to be equal for all times, and then the sine terms have to be equal for all times. And when you look at the equation, then you see now that the sine term, if we now circle them out, these terms here, there is nothing on the right-hand side which has a sine. So that means that we are going to require that this term is equal to 0 for all times. So this is a solution which has to hold water for all possible times. And what we are doing now is to equate the left-hand side and the right-hand side. So there is a cosine side on the left-hand side and the right-hand side, and they have to be the same for all, they have to equal each other for all times. So we get an equation now, which we can actually solve. And that's the key to everything. So if we take this sine piece, so we have an omega tilde of a sine of delta, and then we have minus 2 gamma of omega tilde cosine delta, and this is plus a sine delta equal to 0. So that's one requirement, and then we have the one with the cosines, but let's just take this one first, because that's going to be the key to the solution here. So what we do next, we take this equation here, divide by cosine on both sides of cosine delta. So that gives us a tan delta. So what we get then, when we reorder, this gives us that the tan delta is equal to 2 times gamma of W tilde of 1 minus omega tilde squared. This is just you reshuffling the equations. Does everybody see that? Does that look okay? The next thing we are going to do now is simply to go back and look up trigonometric relations for cosines and sines in terms of the tan function, the tangent. So one thing you may remember is that sine of delta, which we will be interested in, is actually given by tan delta divided by a tan of delta squared minus 1. So what I can do now is actually to plug this one into here. So what happens then is the following, because we also know that the cosine delta is equal to 1 cosine delta squared, or 1 minus sine delta squared. So if I find sine delta, I can find cosine delta. And why do I need these things? Because now I have an equation up here. So if you look back at your equation, what we have is we have a cosine delta here, a sine delta, and a cosine delta. So I can then actually go back and find the value for D by now finding sine and delta and cosine in terms of these parameters, gamma and omega. So when I manipulate these equations here, what you would find is that sine of delta is equal then, when I'm just setting up the answer. So I'm taking the liberty of not going through all these small gritty nitty details. So this is going to be 1 minus omega tilde squared plus 4 gamma squared of omega tilde squared. So it doesn't look that exciting, does it? Then you can get the same with cosine. So if I use the relation which we have here, I just square that one, take 1 minus the squared equation here, then I can find cosine delta, which then is going to be equal to 1 minus omega squared, and then squared here, and it has the same denominator, 1 minus plus 4 gamma squared, like that. So there are some small details. I mean, so I hope you see the wood for the trees here, because some of these details the derivations are not that exciting. So I just want to give you the expressions, because the next thing we're going to do now is to put in sine delta and cosine delta back in this equation with D. And we're going to equate that one with F times cosine. So when you have these two terms, sine delta and cosine delta, the thing which we do is actually to go back here, and we are going to plug it in here. So we've already found that the sine terms which you see here, they have to be equal to 0. So we are going to plug in these equations in here, and then put that equal to F0 times cosine omega of tau. So we plug in sine delta and cosine delta into that equation. And when you do that, so if you insert it back, so insert back, into the differential equation, into the ordinary differential equation, what you will find then is that this coefficient D is actually equal to F0 tilde divided by 1 minus omega tilde squared, and this is squared again, plus 4 of omega squared of gamma squared. And that means we can also find this delta. This is just the tan inverse of 2 gamma of omega divided by 1 minus this omega tilde squared. So that means that we have a way to determine the particular solution in terms of the constants of the differential equation. Now, remember, keep in mind that this is the particular solution. It's going to live together with the homogeneous solution. But what we will see now when we run some calculations is that it is the particular one which is going to dominate. And it will dominate in different ways. So one thing you could think of is that you apply an engine which has the same frequency as the frequency of the system, this omega 0. So let's see what happens in that case. So if I put this omega 0 equal to the system, the applied. So if you look at the specific case, omega equal to omega 0, that means that this omega tilde is just equal to 1. Then this constant D is actually equal to F0 divided by, and then I get the square root of 4 times gamma squared. So this becomes simply 2 times gamma. And this is actually interesting. If you now remember that gamma was given by this constant B, which had to do with the friction of the system, divided by 2 times the mass, and actually contains this omega 0. So let me just bring this down a little bit so you can see this D. So remember now that the solution, this X particular here, of tau, is given by D times cosine of omega tilde of tau minus this delta. So suppose now that you have tuned the frequency of the applied engine to the frequency of the system. What would happen if I make, suppose now this mass very, very large? How would the amplitude behave? What is your feeling? if you now look at the expression, so you know the particular solution, the cosine is not very exciting. That just swings back and forth, right? So that is just something which swings back and forth. And then you multiply something which swings up and down the same dull way. It's almost like my voice. And then multiply with a constant, right? So what happens if I make this gamma very small? What would you expect as a solution? Yeah?
The amplitude gets really large.
Yes, it just keeps increasing. Let's check that, right? So let's see that what we see from the mathematics agrees with what we see numerically. So let's just switch back to the Jupyter notebook. And then, so let's do that. And then we are soon going to end here because I wanted to say a little bit about the midterm as well. So let's take a look at the Jupyter notebook here. And here I have in the lecture notes, this is actually what you will find in the lecture notes. And let's now say, if we have gamma equal 0.2, and now we are going to put, so gamma is not very small. I put omega equal to the natural frequency of the system. Let's try to run this case. So you see the differential equation. I have the acceleration, which is now given by this gamma times the velocity, and then I have x, and then I have this applied force here. And this has a time times this omega tilde, which now is equal to 1. So this is the case which we just discussed on the whiteboard. So let's just run it and see what happens. So this is actually what happens. So I gave it an initial condition, which was equal to 1. And you see now it starts with 1. And then it has a gamma, which is less than 1. So this means that if I didn't have an applied engine, it should start damping it. But then the engine kicks in. And what you see then is that after some time, it's the engine which dominates the way the system is going to oscillate. So that means that your beginning is lost. And everything is now dominated by the particular solution, right? Does that sound reasonable? I think it's very nice to see these links between the mathematics and what you get when you can visualize. Now, the next thing we can do now is just to check. If I make this gamma very, very small, will my solution just blow up? So let's convince ourselves that we're actually going to do that. So let's just do that. And so I'm just going to make gamma very small. So I suppose like this, see what happens. Yeah, this is what we see. So this is pretty nice. So if you're going to make an engine, suppose you want to, when your car and you drive on the Michigan roads, which are famous for their potholes, you obviously have to tune your car so you get some kind of damping, right? So clearly then you have to make these ways to meet the potholes so that you actually have a kind of frequency which matches the kind of shocks your car may actually have when you drive here. I only have a bike, and actually I hit the pothole with my road bike. I didn't pay attention to it, and that was pretty bad. So my front wheel was just ruined. I was able to unclick the pedals fast enough so I didn't end in the ditch, but it was not nice. Okay, that was a digression. Now, what I wanted to say something now about is also about the midterm, the 3 small things I wanted to say something about. So one thing which I've seen, and this is about the, well, let me just do that and change this one because I have it here. So if you go back a little bit and you look at the midterm, there's one thing I wanted to remind you of. So when you look at the potential here, so this is one thing. When you now are going to write a code which simulates the motion here, remember that the force is the derivative of the potential minus. Because I've seen many of you, when you've been writing the code, you actually had some problems with the solutions being wrong because you forgot the minus sign. Okay, that's one thing. So how many of you have seen the solution just blow up? Or not? I met somebody who actually had that problem. Okay, so that was one thing. Now, the other thing which I've gotten questions about is the second exercise, and in particular, how to find the initial conditions so that your motion becomes a circle, right? So you have the expression for the acceleration, right? So let's just bring up that expression. So you have in 2 dimensions, you have this expression here you should get. So this acceleration here, when you are actually computing I wanted to remind you of one thing. So let me just bring up the whiteboard again. So let's remind you of one small thing, because somebody was a little bit unsure about that. So suppose now that your acceleration, I'm not solving the problem for you, but I'm actually putting up, suppose now the acceleration goes like this r squared, or rather the potential goes like r squared. So let's just say the potential looks like this, r squared times some v0, okay? Your potential has another term which goes like r to the power of 4. So when you take when you want the force in the x direction, you need to take minus dv dx, and the same in the y direction, minus dv dy. And then you need to remember that r is equal to x squared plus y squared. So that means that here you need to take the derivative of minus v0, and then you would have the derivative of d dx of x squared plus y squared, right? And that becomes simply minus 2 times v0 times x. And then if you do the same thing here, you're going to get that this is equal to minus v0 times y. So how do I translate that into the vector r? Because the acceleration, remember that the potential is a scalar, the acceleration is a vector. So, because we are taking the gradient, and if we now remember that r is equal to x of I plus y times j, then you see that the force, which is equal to f of x times I plus f of y times j, that becomes equal to minus v0, and then I have x of I, and there's a factor of 2 here, plus y of j, like that. And then you can rewrite this as a minus 2 times v0 times r. So in case you were a little bit in doubt how you got back the vector, so this would be for the r squared term. Then you have a r to the power of 4 term, which you also have to think of. I'm not giving you the full answer. Now you can rewrite this now in terms of the unit vector. So to get the unit vector, you multiply and divide by the absolute value of r. So if I take this term here and simply multiply with the absolute value, r times r, this is then equal to 2 v0 times r, and then we have this unit vector like this. And then you would have to do the same thing with the r to the power of 4 term. So just keep that in mind, and remember the minus sign when you take the derivative of the potential. It's easy to forget that. Then I wanted to say something about circular motion. So you actually asked, what are the initial conditions for circular motion? So how should you fix this one? Any good suggestions? I mean, what does the acceleration look like? So this is actually you rebooting your memory and go back to physics 183. I didn't say goldfish memory because I am the one who has a goldfish memory and you are too young to have that. So do you remember what, if you have circular motion, what the acceleration is normally called then? Yeah. Yes. So you have the centrifugal force, and that means that your acceleration is given by v squared, the velocity, divided by r. So that means that you can fix the initial velocity. So if you go back to physics 183, what you would find then is now that the acceleration A is now, and now I'm looking at the absolute value. That is given by v squared divided by r. And this r would now in this case be an r0, because now if you have circular motion, the radius is the same all the time, right? It can't change. So this, if you now fix r0 to a specific value, you can then find the initial velocity. And that's what you need. So that means that what you need to do now is actually take the acceleration, which you have in the exercise, and equate that one with that expression. So you have an expression for the acceleration in the exercise, and then you simply plug that in. Does that sound reasonable? In that way, you fix r0, which is the initial condition, and then you find the velocity, which you need to fix as an initial condition for the velocity. And with that, you should get circular motion. Okay? Final thing, and that's about the last exercise. So the last exercise, when you look at the potential, what you need then to think a little bit about when it comes to energy conservation. So you can take the curl of the force and show that that's zero. But when you want to demonstrate that energy is conserved, you should calculate the energy as a function of time in your code. So in the last exercise, energy, you show that the force actually conserves energy, but you should actually show that the energy stays constant as a function of time. So that means that with the acceleration, now the velocity you have and the position you have, you can calculate the potential energy at every time step and the kinetic energy at every time step. And when you add these two quantities, you should get something which is flat, which stays the same. So let me just show you that, how you would do that. So let's go back to the Jupyter notebook. So this is a small hint about the last part. So in the last part, you have a potential which looks like what you have here. So you have the potential is up there, and then you have an acceleration which now is given by the force divided by the mass. And in this case, we just put the mass equal to 1. So when you do this, this potential is a little bit steep on one side. So what you will see is that the velocity at the turning point can be a little bit delicate numerically. So you would need a very fine time step. So the solution depends, since we're doing this numerically, depends always on the time step. So one thing you would do then, typically, is that if you look at this code example, so in this case, I've set up the kinetic and the potential energies, and I have the initial conditions as it's an exercise. I set up my initial kinetic energy, which is 0, my potential energy. And then down here, I actually calculate the kinetic and potential energy. And if I plot the energies now, what you're going to see is something like this. So I'm now looking at the energies. And this thing here is actually something which depends a little bit on how you integrate or you define your delta, but you see this is the relative error, which is 10 to the minus 6. This, so the relative error is on the size of 10 to the minus 6, so it's small. I'm blowing it up here. And the thing you see here, this kind of small spikes, is because the velocity changes abruptly at one of the turning points when it gets 0. So this is a case when the potential gets very stiff and you get this sudden change. It's still close to 0. It's 10 to the minus 6. So if you look up in the corner there, it says 10 to the minus 6, right? So if I plot, if I make this small and smaller, you would see now if I make this much smaller, the delta t, if I decide to make it even smaller, you will see then that the arrow becomes even smaller, and it's going to take. And now you say you have 10 to the minus 8. So that kind of spike which you see, that's a kind of is a problematic point when it changes to 0, and then it starts rolling down again to the other side. And these small changes give a little bit small spikes here, and that's going to lead to some kind of small numerical inaccuracy. But I can live with an error of 10 to the minus 8. If you say your error is 10 to the minus 6, 10 to the minus 8, I am happy. So this is an example that energy is conserved. So you can also plot the total energy and just show that that is flat. Okay, I'm going to stop here. I think I went a little bit longer, but I thought we could just spend the rest of the time discussing the midterm. Julie and I, we will just float around here, and George is the online guy. You should feel free to ask as many questions as you want. Never hesitate. I hope these hints were useful. I'm going to stop the recording. I'm going to stop the recording for